and integrated power delivery, and applications in edge inference and chiplet-based systems. So she's the author of a book on on-chip power delivery and management. She is a recipient of the 2022 Google Research Scholar Award, 2023 NSF Career Award. She is a true rising star in the EC department at UIC and a great speaker. So thank you very much for making the trip.
Thank you so much. It wasn't very long trip, pretty local. Thank you so much for inviting me. We'll see how it goes. So on the slide that Natasha presented on all the collaborations and all the different areas covered by the ideal, there was no computer engineering. So let's see how this goes. I had, when Natasha invited me, I had two topics in mind. I decided to go on analog AI. I will maybe tip a little bit on another topic that we are working on that actually involves large models, and we're looking to large language models and then generative adversarial network and all kind of big advanced machine learning models as I speak. But the main idea is going to show you, the main goal is to show you that there are actually a lot of interest and need in smaller machine learning models, but designed differently. So we need them to be very, very power efficient, very compact, very fast, and accurate enough. So I imagine that when I say artificial intelligence, most of you have in mind cloud-based AI and big data analytics and LLMs and all of these very, very important applications. But there are several challenges with them. So first challenge is how much energy they consume. This is a graph that I took online. This is from Wells Fargo, predicting how much energy the AI training and inference, so you have training here in darker color and inference in lighter color, is going to consume over the next few years, not that long, like it's up to 2030. So you can see that the rise is incredible. The inference portion is very, very significant. And we get to hundreds of terawatts hour here, while the total US electricity demand today is 4,000 terawatt hour in 2023, right? So this is actually a big problem with all the consequences on the environment and other problems, and just providing this much energy for training and inference. UIC doesn't have the US doesn't have the tools to enable this today. Definitely working on this, but this is challenge number one. Challenge number two is, while LLMs and big data analytics are very important and already today taking and expected to take significant portions of the market size, right? So we're talking about hundreds of billions and more dollars. They focus on very specific applications, right? We're talking about natural language processing, recommender systems, social networks, not to diminish the importance of these fields, but if we're looking into other AI applications, such as ECG anomaly detection, or fall detection, or hearing aids, all kinds of implantables, wearables, wildfire monitoring, this is also very, very significant applications. And while the market size share is a little bit more modest, it is still very significant. So, for example, for edge computing, we're talking about tens of billions, maybe hundreds of billions dollars within 5 years. And then again, the importance and the added value that these applications bring is very significant. Now, what is unique about these applications, why these are other AI applications? They need to be very, very low power, right? If you have implantable inside somebody's body that operates on a battery, you don't want to perform surgery every 1 year or every other year on the person. to replace a battery. So very, very low power consumption, portable, wearable means very, very small, fast typically, and often secure. This limits the access, for example, for cloud and other problems that we have with our typical AI applications and hardware. On the other side, they typically run simpler AI tasks. We do not necessarily need LLM models to analyze the sensed signals, to do some sensor fusion in health monitors, and they can mitigate somewhat lower accuracy. So if GPU can do an amazing work on a simple task and get us 100% accuracy or 99.9% accuracy, maybe 90% accuracy is good enough for the tasks that we are looking for. So I want to introduce you to this different types of AI applications and talk about these challenges and solutions in this field. So just to put this in this perspective, what happens if we do use our off-the-shelf state-of-the-art hardware, GPUs, CPUs, TPUs, FPGAs, and even ASICs, so application-specific circuits, so systems that are designed with energy and throughput and area in mind. What happens if we use them for the simple AI tasks that I'm talking about? So here we have energy per decision. For example, let's take MNIST data set. This is a quite simple data set of 10 digits, and we need to classify basically multi-variable classification to say what digit it is. So if we use GPU, FPGA, TPU, we're talking about microjoules of energy per decision. Well, maybe if it's very specific, designed for a task, maybe hundreds or maybe even tens of nanojoules. If we're talking about analog alternatives, we're talking about picojoules, tens of picojoules, maybe hundreds of picojoules. This is several orders of magnitude less energy per decision. This is priceless for implantable, for example, applications. If we're looking into size, this is the sizes of typical systems. So we're talking at least about tens or hundreds of millimeters square compared to just a few millimeters square. Again, a critical parameter. Throughput is also very important in these applications. The digital hardware is doing very good with throughput, but analog can do even better. And then in terms of the accuracy, of course, here we see outstanding performance on a simple task. Here, less, but maybe sufficient. So what we want to do, we want to see how we can use analog circuits, analog hardware, facilitate all these advantages, and possibly address the lower accuracy. So the bottom line, different AI applications require different hardware, and in this talk we want to focus on applications that can be facilitated with analog hardware. So low power, embeddable, fast, and hopefully accurate enough. So what I'm going to do is I'm going to give you a very short and very simple tutorial on analog AI. Not sure how many of you familiar with analog circuits, transistors, and all this messy design workspace. And then I'll talk about online training as a very promising tool to solve some of the challenges that I will raise in the first part, and we'll summarize there. Okay, so the target applications that I'm talking about, and not only them, right? Large language models as well. They have very massive matrix multiplications. Two very common machine learning operators in the target applications are single matrix multiplication or convolution operation that requires multiple matrix multiplication. So it's a lot of multiplication and addition. Multiplication, accumulation, MAC operation is our target operation that we want to optimize, that we want to make sure that it consumes little power, that is compact, and it's very fast and accurate. Now, if we're looking into digital von Neumann architectures, we have a processor and we have a hierarchy of memories. Some memory levels are closer to the processor, some are further away, and I think this, you feel comfortable with this information that memory access is a very, very significant bottleneck. So it's not that processing doesn't take space and energy, it does, but access to memory for AI applications can take maybe 3-4 times more energy and time in terms of the delay than the processing itself. Now, there are memories that are very, very local. We can have a capacitor and store some information on a capacitor. This is cheap in terms of the area and in terms of energy power consumption and in terms of the delay. And then there are memory that is semi-local, shared memory like SRAM, and then we can have off-chip memories that access to which is very, very expensive. So memory is a bottleneck, number one, and then that we want to solve. And then another one is, of course, we want to do the multiplication, the processing itself as fast as possible. In general, inference is challenging in resource-limited systems, and not only in resource-limited systems, but training is always more challenging, right? There are significantly more operations that need to be performed, and there are a lot of constraints. So just keep it in mind. In applications of interest for this talk, training is typically offloaded to cloud, performed online. So we train our model, then we upload our model to the analog device. And this is the analog device with the predefined model that we don't have a way to change, that we would use to sense something, to embed, to sense some movements, to sense fires, etc. So this is once trained, done. Okay.
Question.
Sure.
So here, were you thinking specifically of, for these ML applications, were you specifically thinking of the attention mechanism? The reason I'm asking is, in attention, for example, it's matrix multiplication, but they are lopsided matrices, right? So I was wondering if in your use cases,
so there are different. So this devices, the circuits will be application specific. For example, if it's indeed the gesture or some attention kind of, maybe spiking neural networks would work better. And this is actually where I think there is a lot of room for collaboration. People like me who are doing this kind of research need strong expertise in machine learning models and understanding what kind of machine learning models and architectures can be used for within the limitations and advantages of analog circuits. Right? So, for example, in this talk, I'm going to talk about the single-layer perceptron just to demonstrate how we can do multiplication and accumulation. But there are ways to extend it to more complicated systems. For example, we show how we can do convolutional neural networks with the same approach. And this is very, there is a room here for collaboration. We're always after identifying new machine learning models, more advanced, more complicated models than the simplest ones that can take advantage of what analog can offer. Okay. So this is the digital architecture. Now, how the typical analog architecture looks like? You have an analog processor. It gets analog input. Analog means continuous, right? When we're talking about digital, you have either 0 or 1. Each signal can be or 0 or 1. Yes, you can take 64 of them, or 32, or 16, and say, this is my single number. This is what I need to represent my single number. But eventually, every signal is either 0 and 1. In analog, ultimately, every signal can represent a number, any number, as accurate as you want. So it's a continuous range from zero voltage to maximum voltage, and anything between them can represent a number. So this is your analog processor. We can have digital memories. This is the baseline. This is where we start. Analog processor, regular digital memory, SRAM or DRAM, on-chip, off-chip. And that means that every time that you access the memory, you need to convert from the digital domain to the analog domain and backwards. This is a very, very expensive operation in terms of the area, in terms of the power consumption. The other way is to actually get rid of the converters and use different types of memory. So a lot of research that looks into inference in the applications that I'm talking about looks into memory. Emerging memory technologies that allow us to store analog data in the memory. That means that we do not need the conversion anymore, and that's significant saving. We can take it even further. Oh, did it by itself. We can take it even further and collapse the compute and memory and have compute in memory. So we can develop memory approaches where we store and compute with the same blocks. Okay. This is related to memory. Now, related to processing, let's look into multiplication, which is a basic operation that we need to perform. A digital multiplier, 4-bit multiplier, has 712 transistors. Just to align the fundamentals, transistor is a basic building block in all the systems, digital or analog. Typical chips have billions of transistors today, many billions of transistors, and they're switches, right? You can think about it as a water faucet with some handles. You open the handles more, you have higher water pressure. You control the controllers on your transistor, you get higher current. This current can be accumulated in a bucket, like water can be accumulated in a bucket, current can be accumulated as a charge on a capacitor, and from there you take it. Bottom line is the digital multiplier of just 4 bits has 712 transistors, but in analog domain, you can do the same multiplication ultimately without quantization, without any limitations of resolution, with a single transistor. So you can imagine the added value in terms of the area and in terms of the power consumption. So you can think about digital as providing you drops. So every transistor either provides a drop or doesn't provide a drop. This is all information. There is no richness of information in a single transistor in digital. But in analog domain, it's your water flow, and it can be controlled precisely, and it can be higher or lower. So there is a lot of information that can be provided with a single transistor. And this is the added value. The consequences, analog multiplier is much orders of magnitude, many more power efficient, typically much faster, takes much less area. On the other side, the digital multiplier is very accurate and much, much more robust to noise and non-linearities and all kinds of variations, because it's either 0 or 1. So your chances to get it wrong are not very high. This is abstractly talking. Okay. So as I mentioned, most of the research focus on inference for these applications, that's for sure. A lot of research focused on memories, basically analog memories, compute in memory that would allow efficient inference, eliminate digital to analog, analog to digital conversion, eliminate the need to access memory that is located elsewhere. The problem with these non-volatile memories, emerging technologies, that they all have very slow update speed, and therefore for training purposes, it simply cannot work, right? So we still need to train a lot of data, to process a lot of data. We need to have very fast access to memory. So for training purpose, we stay, even if we do analog, we stay with a digital memory, which means we need digital to analog and analog to digital converters, and that's a problem. So here's an example how a chip looks. This is some kind of machine learning classifier. You have your multiplier here, and you have the converter that converts. So area-wise, you can see the difference, and power consumption-wise, it's significant. It consumes the most of the energy in the system. So this is the problem. Data conversion remains the bottleneck. Okay. So what are the opportunities and challenges that we have here? Let's summarize. Significant efficiency, speed, area advantages, potentially there, but should be realized. Accuracy is a concern. Yes, it's there, but potentially can be addressed and should be addressed. There is a very, very big problem of sensitivity to variations, non-linearities, because you have so much information. Right? In digital, it's either 0 or 1. But here, 0.4 is not the same as 0.41. It's not the same as 0.38. So this is a big problem, and this is where I'm leading eventually, how training on chip, online, can actually help us with this. And again, there are a lot of variations, a lot of nonlinearity in analog domain. For example, manufacturing process introduce variations in the sizes. Think about you trained your model offline, works perfectly. You design the chip, you upload the model, but now chip number 35 is different just a little bit, 10% variations, different from chip number 67, but they have the same model. Now, the same model, that means the same weights, the same voltages that are applied to transistors that now have different size. Right? You have larger faucet and smaller faucet, but you use the same control that you pre-trained. Yes, Natasha?
These variations, is this akin to noise? What I would think of as I don't know, can this be modeled probabilistically as some kind of...
Oh, they can, yeah. There is a typically normal distribution. If you look into within a single chip, there is a normal distribution, and then chip to chip, there is a normal distribution in process variation. This is the same variation we're talking about. But there are others as well. There are noises in voltage. There is, for example, if your chip is working hard, it warms up. The temperature rises, it affects the ability to conduct current of all the components. So there are all kinds of noises and nonlinearities and voltages that needs to be mitigated. Okay, there is another problem, and that actually relates to the second topic that we are working on in the group, and I won't be covering in detail today, but I'm happy to collaborate on this. This is a very, very large pain that this is a bottleneck for analog AI to really emerge and shine. And this is design and simulation. So design and simulation tools for analog circuits exist for many, many years, but they just cannot mitigate the computational and memory complexity required for simulating AI systems. Just as an example, for a simple data set, I design an analog circuit, and I want to see how it performs on a simple MNIST data set. So MNIST data set, each image has 28 by 28 pixels. I cannot simulate it. We need to downsample the image to 4 by 4 approximately, just 16 bits of your input, and then classify based on this. And there we say, okay, we only get to 80% accuracy. Of course, we downsampled it to nothing, right? So if we compare it to the performance of a digital quantized system with 4 bits, we perform better than it. Okay? So we basically need tools, and there is a lot of need for AI assisted, AI enhanced simulation tools, and this is where we're looking into generative models that predict the performance of analog circuits and large language models. So this is a separate research. Okay, now I basically want to touch upon several issues.
Yes. About the challenges, I'm thinking like for in-memory computing and those sort of, it's a very promising direction. But the concern is there any security concern? Say, if data is lost when you put the data in memory, and the RAM could be very complicated when you handle both storage and also compute.
So there are different approaches. For example, loss, you mean loss of accuracy, loss in what?
The data, the hacker to hack the
That's
data.
why there is a lot of emphasis on developing non-volatile memory. So there is ASTRM, there is compute in ASTRM that was probably one of the first papers in the field that show how we can compute in memory, and that was ASTRM based. ASTRM is volatile memory. There is a problem like you shut down and things happen for sure. Again, keep in mind the applications, right? Keep in mind that machine learning models, they are somewhat forgiving for errors, right? If your weight is a little bit here or there, but yes, this is a problem, and therefore the training online approach that we propose, it actually addresses everything. Well, it gives you the opportunity to train, retrain. It addresses a lot of non-linearities and variations issues. I'll talk about it. It allows you to design with less constraints. Your accuracy goes up. It's really, it's a good idea. Okay, we'll get there, but definitely. You can add it to the list of non-linearities and variations and issues, everything that contributes to errors.
On-device training, the power is also could be an issue, right?
Power?
Yeah.
How much power it consumes?
Yeah. You mean
Nothing.
on-device training?
It's nothing.
Okay. Okay.
It's
For
nothing.
on-device training.
It's nothing.
Okay.
Okay. If you, I'm getting there. If you challenges that we deal with, actually very, very much similar. I took notes that I should try this and that in terms of quantization when you gave your talk. So resolution is ultimately unlimited, but not really. Because of the noises and non-linearities, we cannot assume that 0.3 and 0.305 are different values. So what we do is we quantize. We take the range of voltages, and voltage here, every voltage represents a number. So for a single signal, we take the range of voltages from 0 to the power supply that we provide, and we quantize it. So we can choose 4 bits or 5 bits or 6 bits, and therefore we will have 2 to the power of 4 minus 1 levels, and this is our levels. So it's not truly continuous. Effectively, it is somewhat limited. Maximizing resolution is critical. Same, right? The more we quantize, the more data we lose. We are interested to keep as much data, but here's the trade-off: beyond certain level of voltage range quantization, it's not going to work. So we use additional methods to increase resolution. For example, so remember our faucet, water faucet, right? That is controlled, for example, here by the weights and here by the features, and the current that will flow is going to be proportional to the multiplication of the two. So, for example, one way to increase resolution is to have positive sensing line and negative sensing lines separately. So we have negative weights feeding into one line, positive weights feeding into a different line, and then we can compare. The charge is accumulated here. This is like summation. So everything that happens on this line is, think about the current that flows through this transistor is proportional to the weight times feature. And through this one is weight times feature. And then all these currents accumulate, right? The water flows to the same bucket. You have this bucket that comes from the positive weights, have this bucket that comes from the different negative weights. We compare the two. This is our regular solution, right? Basically, we define the regular linear classifier with pluses and with minuses separately. So there are many this kind of tricks that we can do to increase, for example, resolution. In general, digital circuit design is, once you have the architecture, it's actually mostly about electronic design automation from there. You have tools that just take it step by step until fabrication. I know I worked for many years in IBM as a digital circuit designer. It takes all the way to manufacturing, you are done. Analog circuit design, it's like a magic. It's a black box. It's a huge space of options. You can use different. There's no way to design a multiplier or any other function, and it is really a Lego that you need, or puzzle that you can build in different ways. And there are some ways are better than others. Okay. So, for example, we use a lot of tricks. There are a lot of tricks we can use to effectively, for example, increase resolution. This is just one example that we used in one of our work. In the other way, for example, is you can use. This is a standard transistor, but there are people who work on devices. They invent new transistors, new transistor technologies, and now there is a lot of effort to design transistors, to invent transistors that are actually AI friendly, right? That have some characteristics that would be beneficial for AI applications. For example, the current can flow into both directions, so now you don't need two sensing lines. You only need one, and you can either charge it or discharge it with the same device. So we have a very nice collaboration with a few professors from UT Dallas and UT Austin who invent transistors, and we enable them for AI. We do design with these transistors. Yes?
Why does separating these two lines increase the resolution?
In terms of the weights. So now you do not need to encode negative weights and positive weights on the same voltage range. You can use the same voltage range, right? So if you divide it in 16, let's say, levels, so instead of saying weights from -5 to 5 map into this 16 levels, you say 0 to 5 maps and 0 to 5 maps. So you effectively get high resolution.
Thank you.
Sure. Okay, another issue that we have that is probably less of an issue with digital is linearity. We need, when we say that the current is proportional to a function of A times B, this is nice, but what exactly does it mean, and what other terms we have in this function? So what we get is typically some kind of semi-linear relation, and we want to make it more linear. Now, one approach is to focus on a smaller range, but that's going to hurt our resolution. So we want the range to be as large as possible of values, but still it should remain linear. So we have all kind of pre-processing and circuit level techniques that we can use to address this kind of issues. So this is an example also from our work. We decided to use a transistor where the weights were applied to the gate here, and the features were applied to the body bias, never mind, the different terminal here. And what we saw is that the current is actually proportional to exponent of VA square root of VB. So the way we took care of this is we did some pre-processing linearization. We trained the model with square root of features. So we extracted the features, we took the square root of features, we trained the model with this. So basically now our model knows to our weights know how to work with square roots, which is eventually what will be seen on chip because of this relation. And then we logarithmically adjusted the model to get rid of the exponent when we actually see these values on chip. So this is kind of pre-processing. In a different approach, this is the AI-friendly technology with our collaborator from Texas. We saw, for example, this kind of relation. Yes, the VA times VB was there, but there were additional terms. So in this case, we can do some circuit level solutions when we basically, on both lines, get terms that cancel each other without going into details. Just want to give you a little bit of taste of problems and solutions that we are looking at. We have quite a few systems that we implemented and compared and showed different ways. This is just one of them from 2021, where we designed a 10-class classifier with all the components to work on the MNIST data set, and this is some of the results. So what we simulated in Python was 92% accuracy. What we got eventually is 92% accuracy. And we're talking about tens of picojoules. And we're talking about now this is actually per max, so you need to multiply it by 45. Per binary classifier, this is per binary classifier, single classifier. We have basically 45 of these classifiers, and then we have some voting systems to choose the right. So this needs to be multiplied by 45, maybe 50, but still very small, nothing compared to digital, of course. We never compared to digital in our works, but in terms of the accuracy compared to other analog works, this is also a very good result. So this is for binary classification for inference online. Okay, so now let's revisit this slide from previously. Significant efficiency, speed, area advantage, they are there and they can be realized. Accuracy is a concern, but here we can do 92%. This is sufficient for many applications. We just need to understand what applications are happy with this accuracy. A big problem is sensitivity to variations. So yes, we show this result, and this is average accuracy. But if we run Monte Carlo simulations, which take into account all kinds of mismatches, all kinds of variations, noises that can occur in real devices, we can see up to 20% drop in accuracy. Now, 92% is very nice. 72 is not that great. So, and actually, if you look into state-of-the-art publications in this area for inference, they mostly do not talk about variations, about their accuracy under variations, because there is really not much to say, and many say it's a fundamental issue of analog circuits, and this is what's going to limit. We say that's not the case, actually, because what we can do, we can train online. If we train online, then the model is inherently, naturally adapts to whatever variations. Either it's process variations, the transistor is a little bit larger, a little bit smaller. As the signals propagate, forward pass and backward pass, they take into account all this information inherently, and the model is exactly right for the device. Not only for the device, but if we retrain, if something happens, there is a voltage, local voltage drop, supply drop, there is a temperature rise, any kind of noise, different environment, it's going to account for these changes.
And how often you have to train them?
Perfect. We can do at the very least 100,000 inferences between retraining. So retrain is in the order of second, one in half a second, one in once, and so we're talking about hundreds of milliseconds for retraining. And the power of training is not that large.
I mean, how often then you just retrain once? And then
You retrain, and then you can do after this, you can execute over 100,000, so 100 to 200,000 inferences before your model. So now, again, this is specific to the system we designed, because not only we're doing training, because we're doing online training, we can afford having local tiny memory near the transistors. Our memory is a single per bit is a single, not per bit, sorry, per line, per multiplier basically is a capacitor, right? That per weight is a capacitor that accumulates this capacitor. We train, we change the voltage levels to the right levels, so the system works, and the accuracy is good, right? I'll show you how it saturates, and then we can use it for some time before it discharges. Capacitors, because it's small, it's effective, it has leakage, it leaks, and then over time it loses the charge. But within this time, to get less than 0.5% accuracy drop, we can do over 100, it's actually 200,000, but we're staying always on the safe side, 100,000 inferences until we get 0.5% drop in accuracy. So a lot. And I will show you that the cost of the training is not that much in terms of energy. So over 100,000 inferences, it just disappears. But just as itself, it's not that much. Okay. Right. So this is what we propose. This is a system. There are small trainers here. I'm not going to talk about circuits, no worries. But basically, there is some kind of training circuit with inference learning. Now, this training circuit reuses significant portions of the inference circuit, so all the multiplication happens through the same components. So it's very efficient from this perspective. And then we use, I did copy paste yesterday from the paper, so this is where the figure, number 8 and whatever from, just ignore it. Okay, so we have tiny multipliers and tiny storage for weights, no memory communication, no data conversion. We use all kinds of linearization and resolution tricks. For example, for resolution here, we use sign and magnitude data representation. So magnitude is stored over the capacitor. Sign, plus or minus, just stored in a like a digital signal, right? 0, 1. So why do analog? And we have the online training. This is the general algorithm for calculating the prediction and the weight update. All the operations here are analog friendly. We have multipliers, which is analog is great with multipliers and additions. This is mostly what we have. We use the same components, and we are able to do inference and training. So this is basically a single capacitor that accumulates the weight magnitude, and this is a tiny circuit, that digital circuit that tells us whether sign is positive and or negative. There is quite a lot of algorithmical thought behind it to go over different cases and scenarios. But the bottom, this is the multiplier. We use the 2 transistors here for a better linearity. But the bottom line, I want to show you here. Forget that this is the circuit for inference, that the most of it. For inference, you have multipliers here, and then it propagates through some analog circuit, and eventually there is a decision whether there is an error or there is no error. So you can see here, for example, for this original images that we want to classify, here at the bottom, this is the true label, and here's the prediction. And here's the phase, the activation phase, where we actually make the prediction. So it's correct here, incorrect here, correct and incorrect, just to show you how it works. And then for the training, again, this is a circuit somewhat similar that performs the training. Basically, there is backpropagation. You can see that this is the magnitude of the feature that changes, the inputs that we provide to train the model, and this is the error. And you can see that as a result of, so for example, here there is no error, right? So the weight magnitude stays the same, or there is error. And then you can see how the magnitude of the weight is adjusted, right? So I just want to show you the process of adjusting the weight, and the sign is adjusted as well. This is the training results for the individual binary classifiers, and you can see how the accuracy saturates. So, of course, this is not from your Python simulation, but you see the convergence to the value, and most of them is very, very high. Some are a little bit, so some pairs are more difficult, of course, to classify. 8 versus 9 is more difficult to classify than 0 versus 1. But this is binary accuracy. Keep in mind, once we combine it, it's going to be much more accurate, because maybe 8 versus 9 is difficult to classify, but we're going to vote on it. And if it's a 9, then we also have 7 versus 9. We also have 6 versus 7 that are easier to classify, and this binary classifier will eventually provide us the correct information. So this is 100 training samples and 10 training epochs, keep in mind we're super limited by simulation abilities. This is why would I downsample my 28 by 28 pixel image to 4 by 4, right? And giving up on such a huge amount of information. Of course, the accuracy would, and there is no problem with me if we would be able to simulate it. Once we manufacture it, there is no problem. It's just the simulation. We cannot simulate it. We cannot send for fabrication something that we didn't simulate. So this is a big concern. Now this here, we see also binary steel accuracy for model trained and executed on Amnist in Python with 4-bit resolution, 5-bit resolution, 6, 7, and 8. Flames is in the red, in the middle. So what we see is that it's on average better than a 6-bit digital classification in Python. And this is just in the binary domain. And it's on average better. The minimum accuracy, I didn't put it here, is better, and the maximum is better. So it is really quite good. And this is our main achievements. So, for example, look here into mismatch with training or without online training. So let's say we have this perfect model. We trained it offline and we upload it. And now we see how it responds to different variations. So with the online training that adjusts the weights for the device, we have minus 2.21% degradation for mismatch at the worst. Without, not only we have 17%, 18% almost degradation in the worst case, but also the average is significantly lower because of the non-linearities. So not only it addresses variations during the process, for example, of the fabrication, but also it addresses non-linearities. So that are inherent for analog ICs. So this is really a big achievement. Some comparison with recent state-of-the-art work. This is Nature, TICAS, JETCAS, all top journals in this field. This is the accuracy that we achieve for the whole multi-class classifier, high speed, less than 2 picojoule per decision. This is with training. So this is with training normalized across 100,000 inferences. So it just disappears. It becomes negligible. But even if I don't have the number here, but I think 40 picojoule, this is how much training takes in terms of energy. Okay, so I'm a little bit running out of time. Anyways, I'm not planning to go into details of circuits with you, but just to showcase you that this fundamental approach and the building blocks that we developed here can be taken further. It can be applied, for example, to do convolutional neural network while preserving the same advantages that we showed for the perceptron. Just show how to design the forward pass, the backward pass, the kernel update values. And I think I would want to stop here. Again, just to summarize, there is a broad range of applications that can enormously gain from non-traditional digital computing. They require very low power, they need to be compact, they need to be fast, and they need to be accurate enough. They are okay with running typically not LLMs, but simpler models. All of this can be addressed. Really, the key issue with analog circuits, as has been spoken out for many years, is the vulnerability to noise, nonlinearity, etc. I think that training, this is the first work that talks about how training can address these. I'm a true believer that there are still challenges that I didn't go into the details at the circuit level, but I think that there is really a very interesting opportunity here. The simulation is a big pain that remains still. We have a lot of work in this direction, not only us. but it's still there. We were not able to resolve this. So with this audience, I think there are a lot of opportunities from all kinds of perspectives, both on this AI for analog AI that I didn't talk about, but also from really somebody who comes with deeper understanding of various machine learning models and architectures. And if we take it with our knowledge of analog circuits and the advantages, maybe we can identify very important other applications and different models that can leverage the advantages that analog AI can offer. That's it. There are some references, and I wanted to thank all of you. Thank you for listening for me for 45 minutes. And this is my students. Farid is graduated in 2022, I think. He's currently, I think he's already senior silicon architect at Google, working on AI optimization for cellular phones. And Mohammed is my current student working on this project, and my collaborators that work on emerging technologies. And it's funded by National Science Foundation. So thank you for all the parties. Any questions? You're always welcome to reach out for slides and for questions. Thank you.
Okay. Thank you very much. Okay, so we're a little behind schedule, but I still think we should take a 10-minute break. All right, and restart again.